Hello all, this is Siddhesh Nesarikar, 5th year dual degree student from IIT Madras. Today I'll be presenting our work on travel time estimation for emergency medical service vehicles. So what is the travel time for an ambulance? An ambulance have multiple phases in its journey. It could be from base to the incident location to the hospital, or from hospital back to the base, or in between the bases. Base is the point where the ambulance waits for a distress call. Why is this estimation necessary? The first thing that comes to our mind, as it is, that we need to dispatch the ambulance that is will take the least amount of time to reach the incident location. Some other applications would also be the allocation of multiple ambulances that we have in the discrete bases that are spread across the city. We obtain the data for this analysis from 108 Emergency Ambulance Service of Tamil Nadu, from the call records of September 2021. As seen on the image in the right, this dataset consists of GPS trajectories, which are nothing but discrete points with their timestamp and location. We refine this data and extract the incident location and starting and end location of the ambulance to get a dataset of 7 features as seen on the screen. Over here, we see two distances, Haversine distance and OSRM distance. OSRM is open source routing machine, which gives us the shortest road travel distance between 2 points, whereas Haversine distance is the greatest circle distance, or we can look at it as the displacement between the 2 points. Call answered hour is the time of the day at which we receive the call. Travel time is a continuous variable that we need to predict. And as you can see, we have a lot of data points for shorter journeys and very few for the longer journeys, which could affect results for the latter, as we'll be seeing later. It's a standard practice uh, to ignore those calls where the speed of the vehicle is less than 5 km per hour, because this is too less an average speed, especially for an ambulance. So we find some cases in our data set, and we ignore those cases which have an average speed of less than 5 km per hour. We also keep both the OSRM and Haversine distances in our analysis. Although question might arise, why do we do that despite having such a high correlation between the two? The reason is that, as we can see in this figure, for very low Haversine distances, the correlation breaks. That is, the OSRM distance could be much higher than the Haversine distance. This could be due to presence of certain turns and stops that the ambulance cannot ignore, and hence the actual path is much more than the displacement. Now, in the dataset that we have multiple categorical features which are multi-class in nature. For example, we have 35 taluks across 5 districts, and hence the dataset could turn out to be very sparse if we try to one-hot encode them. And this could lead to the models not performing at their best. Hence, for a sake of comparison, we decide to ignore those multi-class features and limit our analysis to only 4 features as seen on the screen. Is Chennai is a feature which tells us whether the district is Chennai or not Chennai. The prediction is limited to only base to scene phase of the ambulance's journey. We start with basic, simpler models like linear regression and lasso, followed by support vector machine. After this, if since we don't get satisfactory result, we move on to tree-based bagging and boosting methods. The results, as expected, we find a somewhat poor fit for the simpler models, but the models overfit when we use random forest or tree regressors. These two are bagging models, but we find a very reasonable fit for the boosting models. And CatBoost performs the best with the least root mean square error and also the best R-square coefficient on the test data. Since we are using CatBoost, it also has an advantage of natively handling categorical features, so that we need not one-hot encode them and feed it to the model. We can keep those categorical features and retrain the entire model again and analyze the feature importance of the same. We realize that, as expected, that the two distances have the highest feature importance amongst all, but we cannot ignore the rest of them, as the others also have some considerable impact. Finally, as we can see in this figure, that for the longer journeys, we are not able to predict with as good an accuracy as for the lower journeys. This can be improved by breaking down the entire route into smaller links and trying to estimate the travel time for the shorter ones, and with a hope to getting a better cumulative accuracy. Thank you.